Sorry about the little technical hiccup. All right, good. Cool, so I'm Walid Krichene, and I'll present our paper revisiting the performance of iALS on item recommendation benchmarks. And this is joint work with colleagues at Google, Steffen Rendle, Zhang, and Yehuda Koren. And I'll try to go a little bit faster to make up for the lost time. So iALS stands for implicit alternating least squares, which is a method for matrix factorization with implicit feedback. This method is very well known. It's been proposed over a decade ago. It's known to be simple and scalable, and it's often used as a baseline in many recommender system studies. However, recent publications have been reporting poor performance of iALS on item recommendation benchmarks, and some of these results have even been reproduced. So as a result, iALS has sort of fallen out of favor, and it's no longer considered as a strong baseline. I think that's fair to say. But our experience has been different, so we wanted to revisit some of these results. So what we did is reevaluate the performance of iALS on 4 item recommendation benchmarks. And we show that okay, I just realized that somehow if I want to share my audio, the slides are paused. So let me try one last thing, which is I will switch to sharing my full window. Okay. All right, so as I was saying, we reevaluated the performance of iALS on 4 item recommendation benchmarks. And what we showed, or what we found, is that with a little bit of care in tuning the model, we can obtain much better results than what was previously reported. In particular, we found that iALS outperformed each of the other methods that we evaluated on at least half of the metrics. So our message in this paper is very simple. We have 2 parts. The first part is that iALS remains a strong baseline, and we hope that future studies will take this into account. And the second is to give some guidelines on how to tune it perhaps more effectively. All right, so in the first part, I'll go over the empirical performance of iALS. I'll very quickly review the algorithm, although I think for this audience, it needs no introduction. But we'll consider a simple matrix factorization problem where we're given a partially observed feedback matrix where each row represents a user, each column represents an item, and there's a 1 in the matrix if there's an interaction between the user and the item. And the goal is to learn a low rank factorization of this matrix, which means that we learn 1 embedding per user, 1 embedding per item, and the model's prediction for this user-item pair is the dot product between their embeddings. And the model is trained by minimizing quadratic loss, which can be decomposed into these 3 terms. So the first term fits the observed entries. So this is a sum over the observed part of the matrix, which is usually very sparse. There's a second term, which is a sum over all pairs. And this can be thought of as a sort of prior that pushes all of the predictions of the model towards 0. And there's an L2 regularization term, which is a sum of the squared L2 norms of the embeddings, each scaled by the frequency of that user or that item. And I'll come back to this loss function when I talk about tuning hyperparameters. Now, regarding the evaluation benchmarks, we revisit 4 benchmarks that are very well studied in the literature. The first 2 are item recommendation proposed by Liang et al. On movie lengths 20 million and million song data. And the next 2 are sampled item recommendation benchmarks proposed by He et al. On movie lengths 1 million and Pinterest. And the details, the exact details of the evaluation protocol are reviewed in the paper. So in this presentation, I'm just going to focus on the results for the first 2 benchmarks, since the qualitative conclusions are the same for the next 2. Okay, so let's look at some of these results. So this first table summarizes the quality metrics on the movie lengths 20 million benchmark, sorted from best to worst. It shows the previously reported results for iALS, which performed quite poorly. But after retuning the model, we obtained considerably better quality. We found that on this benchmark, iALS outperforms methods like SLIM, MoldDAE, and EASE, and it has comparable quality to MoldVAE. And these are all much more recent methods that are considered state-of-the-art. A similar gap can be seen on the million song data benchmark. The previously reported performance is quite poor. I would say it's even worse in this case. And our results show much better performance where only one method outperformed iALS. And again, if we look at the combined results from these 4 benchmarks, we found that iALS outperformed each method on at least half of the metrics. Now you might be wondering, why this gap? So we looked at a few parameters and to better understand where this gap might come from. And one thing that I'd like to show is to look at the effect of model capacity. So in this figure, the x-axis is the model capacity, here measured as the number of parameters per item. And the y-axis is the quality metric, in this case, recall at 20. And so we plot this for iALS as we vary the embedding dimension. So by increasing the embedding dimension, we increase the model capacity. And we compare it to a few other methods that were published, including the previously reported number for iALS in orange here, and other state-of-the-art methods like MoldVAE in green and EASE in red. So now if we compare to the previous iALS numbers, on the movie lengths 20 million benchmark, the gap is quite substantial. And this shows the importance of properly tuning hyperparameters. So here the gap can only be explained by tuning the other hyperparameters of the model. So now on the million song data benchmark, the results are actually in line with what was published before for the same embedding dimension. But now in both cases, as you keep increasing the embedding dimension, we get quite large improvements, as you can see on this figure. And so one could look at sort of this capacity quality trade-off, if you look on this capacity quality plane. And if you compare iALS to other state-of-the-art methods like EASE and MoldVAE, you can see that it's quite competitive. So in some cases, it's better. And on the second benchmark, it's a little bit worse, even though we didn't go all the way to the model size of a method like EASE. Okay, so this previous experiment focused on the effect of the embedding dimension, which is one, I would say, of the important hyperparameters. And this brings us to the second part, in which I'll give some intuition and maybe some guidelines on how to tune the other hyperparameters. Okay, so there's a total of 6 hyperparameters that I'm listing here on the right. And I'll go through the list and see how we can simplify perhaps the parameter search procedure. Okay, so first there's the number of iterations t. So one thing we can do is measure the evaluation metrics after each iteration of training, which means that we can essentially remove t from the search space, provided that we use a large enough value. And ALS is known to converge exponentially fast in t. So typically a value in the range of, say, 16 to 20 should be a reasonable choice for most problems, at least in our experience. Another trick is to save computational resources. We can also do the initial tuning with a smaller value of t. For example, we typically use 8 or so. And this is to get a rough estimate of the appropriate range of the other parameters. And then we can do a more refined search for a larger value of t. Okay, so second, there are the model parameters. There's the embedding dimension d and the standard deviation sigma, which determines the scale of the initial random embeddings. So as we saw, the embedding dimension controls the capacity of the model, and increasing this dimension can lead to large improvements. And from our experience, one of the main reasons for suboptimal results with reported for iALS is an embedding dimension that's too small. Now, of course, increasing the dimension comes with some cost, so both training and serving cost. Because asymptotically, so if we focus on training, asymptotically, the training runtime is cubic in D, at least if you use kind of the vanilla solver. But if you use a method like block coordinate descent, then the runtime will be down to quadratic in D, which makes it, scale to a much higher dimension. For the standard deviation sigma, we haven't really observed much sensitivity within a broad range. And a typical value to use is something like 1 over square root of t. So I would say not much effort should be spent on tuning this parameter. Next, there are the loss hyperparameters. There's the unobserved weight alpha 0 and the regularization coefficient lambda, and these two control the relative weight of the three components of the loss. And I would say that these are perhaps the most crucial hyperparameters, and it's important to tune them carefully. And in general, most of the effort will be spent on tuning these two parameters. So one strategy that we found useful is to do a joint search on alpha 0 and lambda on some exponential grid to find the appropriate scale of each of these parameters. And then we can refine the search as needed. And one rule of thumb is that the different components of the loss should be roughly on the same scale. So they should not differ by several orders of magnitude. And that can give you a hint on where alpha 0 and lambda should be. And once you get their scale right, you can do a more refined search by looking at the quality metrics. Okay, and finally, there's the regularization exponent nu. So here, the effect of nu is that the larger nu means that regularization becomes stronger for frequent items and users. In our experiments, the optimal value was always 1, but this can depend on the benchmark. Here, one observation is that when searching over nu, the optimal value for lambda might also change as you change nu. This is because a larger nu will increase the scale of the regularization term, so lambda will tend to decrease to sort of compensate. And so, this coupling between parameters can make it hard to do the parameter search. So to solve this, we propose a reparameterization, which kind of decouples these two parameters, and I'll refer you to the paper for details. Okay, as a quick conclusion, really again, our main message is that the carefully tuned iALS remains a strong baseline on item recommendation benchmarks and outperforms many of the more recent methods. And besides model quality, there are other advantages to iALS that are not covered in this paper. So for example, there's its scalability. Also, there's fast retrieval using approximate search, which make it a very strong contender in practice for practitioners. And we also saw that even though the parameter space looks at first glance to be large, you can prune it down, and you can use a few tricks to make the search easier. And so, another sort of message is that we think it's important to have benchmark numbers that are reproducible and reliable, because progress in recommender systems is in large part driven by empirical studies and results. And so we hope that these encouraging benchmark numbers spark some new interest in iALS, either to reuse it as a strong baseline or to drive some new research for it. All right, I think I'll stop here. Thank you, and I'll take any questions.
Excellent. Yeah, there's a bunch of questions on Slido. I don't think we're going to be able to get through them all in time because of some of the technical difficulties we had. But maybe the first question was asked was kind of interesting to me because I know that you tuned on a bunch of different hyperparameters talking But one of the questions here is, have you also considered doing any sort of pre-processing on the input confidence matrix that you're passing to iALS? Like, are you doing any sort of normalization, like TF-IDF weighting, to sort of give less confidence to users that like everything versus people that are a little bit more selective in what they've interacted with?
That's a good point. Yes, that can be considered as one extra hyperparameter. In the search space, we haven't done that, and it's quite possible that if we do this kind of exploration, this can, improve the performance even further of iALS and perhaps of other methods. What these results show is that even by tuning the sort of most basic hyperparameters carefully enough, we can get to state-of-the-art numbers.
And just one final question. Someone was asking, what was your tuning budget? And have you tried to tune other methods as well?
Yes, I think that's an important question. So we think that trying to tune other methods will not necessarily do them justice because we trust that the person who invented the method is the person that's more well placed to tune that method because they understand it correctly and they know, for example, which hyperparameters to tune. So in our experience, it's been hard to improve, some of these state-of-the-art methods by trying to tune them ourselves. So usually the inventors of the method will do a much better job on these benchmarks. So we think, we've spent quite a bit of time understanding and tuning iALS. So we wanted to share some of this experience, but it's quite possible that by tuning other methods more carefully, the benchmark numbers will improve on those methods as well. We were just not able to do it.
Excellent. Well, let's thank the speaker. There's a bunch more questions on Slido too that I'm hoping you can answer. But thank you.